Hello, today we're going to be doing a physics question, and it's in topic or theme E, and it's on discrete energy levels. So the diagram shows six energy levels of hydrogen. Describe how an emission spectrum is an evidence of discrete energy levels in an atom. Okay, so so emission spectrums look something like uh yeah. So yeah, ignore this and this. This is just this. The ends is really these four lines. And let's say, yeah, 400 nanometers and 700 nanometers. Okay, so on an emission spectrum, usually there's a few lines, very specific lines, and they show discrete energy levels. Uh, because, uh, I mean, this is how I would answer the question. Um, electrons when electrons in an atom um, get de-excited. So when they get excited, it means like they absorbed a specific wavelength and they jumped from, let's say, the ground state to the second excited state or any excited state here. So when electrons get de-excited, and when they get de-excited, that essentially means they drop down, which means they release that specific wavelength, which is what we see, what specific things we see here. Like it can't go from the fifth excited energy level to like here or here or here. It's not continuous because there's specific discrete energy levels. They emit specific discrete wavelength. Okay. I think it would also be good to mention how the wavelengths or packets of energies are photons. Um, how should I write this? I think just like, yeah, just including photons would be sufficient here. Okay. On the energy diagram, draw an arrow to represent the transition that emits the shortest wavelength. So, I mean, it's important that we know that the shortest wavelength means the most or the greatest energy, because E equals HF. Actually, yeah, I'll do this calculation later. Let's just do BI first. So the largest transition, which is the shortest wavelength, what does it want? Yeah, it's just this. An arrow that represents emit. Yeah, emits is going down or de-excitation. So this should be good. Calculate the shortest emitted wavelength. Okay, so for this, yeah, listen, let's just do it down here. We need the necessary formulas, so E equals HF is definitely one. And yeah, C equals frequency wavelength. Is there anything else? Yeah, this should be fine. Okay, so what do we want? So let's just rearrange the second one. So lambda is what is it, C over F. And let's rearrange the first one for F, which is F equals E over H. Okay, and then, yeah, let's sub that in. So, since it's in the denominator, we just flip it, so HC over E. Okay. So we know H, it's Planck's constant. We know the speed of light, it's a constant. E is the difference. So, yeah, we're just calculating the wavelength. So we just want the magnitude, uh, the negative or positive doesn't matter in this case. So, and this is also in EV, not in joules. So we also need to convert that. What is this? 13.6. Yeah. 13.6 minus 0.38. Okay. And to get in joules, we need to multiply it by yeah, by the magnitude of the elementary charge. And H is Planck's constant, which is 6.63 times 10 to the negative 34. Speed of light is 3 times 10 to the 8. Okay. Yeah. And this should be the final calculation. So let's just put in the simulator here, TI-84. Okay, and this should get the final answer. Is this? Yeah, this seems about right. Okay. 9.4 times 10 to the negative 8 meters. And if we convert this to nanometers, yeah, this is 94. And this is two significant figures. Is that what it wanted the shortest? Yeah. And that's the final answer for B2. Okay, so now let's do C. Emitted red light has a frequency estimation of 460 T. Okay, that's probably a prefix. Hertz, determine which energy level transition emits this red light. Okay. Okay, let's write down what variable we have. We have the constants. We have the frequency. And energy level. Yeah, I guess we just want energy level, and then we can see which one matches up. Okay. So yeah, we just use the same equations basically. So E equals HF Oh, yeah, we only need this equation. Okay. Uh, what is this? 6.63 times 10 to the negative 34. Frequency 460. Okay, what is T? T is tera, so it's 10 to the 12th. Okay. Okay. And now we'll get the energy in joules, so we need to convert it. Whoops. 3.055 times 10 to the negative 19 joules. Okay, so we want this in EV, which means we just divide by the magnitude of the elementary charge. Which is 1.9 EV. Okay. Let's see. So yeah, we need a transition that is about 1.9 EV. So let's just okay, obviously 1 to 2 wouldn't work. 3.4 minus 1.51. Okay. 2 to 3 might work. Okay, yeah. These are obviously too small. And this 2 to 4 would be too large. So I think it's 2 to 3 or emitting, which means 3 to 2. So we can just write therefore um, energy transition. Okay, and that is our final answer for C. And we have completed this question. So yeah, thank you.